Then the కూర్చోండి చేసినాం కొన్ని.
Everything okay also? Okay, good afternoon everyone. Thanks a lot for taking some time from your valuable time and spending with us. I'm very much privileged to have people, particularly those who have contributed to the school. I think I'll start with Dr. Balmurli Krishna. I've heard that he has been, how to say, the first person to teach microscopy, the first batches, so it's very much interesting. And then I have how to say IOE director who have been supporting in several sense, also being team. And then this all happened because of our special guest here, who will be the distinguished how to say person giving this lecture on this Golden Jubilee distinguished lecture series. Probably this might be the last one, I would say, but I am taking this privilege to take the same tag and to take this initiative. And then the first person of the university, our vice chancellor, so I am very much thankful that he is here and he gave us time and I will say the enthusiasm, at the same time inspiration, and also pushing us to do things better and better and improve. So I'm very happy that seeing him here. So with this, I would like to invite all four dignitaries to come on the dais, please. Yeah. So if So there are how to say certain protocols to follow, because actually I want to listen to the lecture. Frankly speaking, I'm somewhere in the middle of this lecture, and in between there are certain protocols to follow. So with this, I would like to welcome you all. And you know, this gold is a FCC, and everything it starts with this beautiful coordination number in the FCC, you know, and we are 12 people in the School of Engineering. I remember this as a few, how to say, years ago that we were 8 and now 12, and that gave us a strength to do several things in the past few years, particularly the initiative of starting the IM Tech program, where I see some of the students. I would have expected the hall full. Probably the way numbers are going, 60 plus 60 plus 60, I expect that hall to be filled in maybe coming years. I would simply say like that. And those who are sitting on the back, please come forward. It's a class where you want to understand more from the speaker. So don't hesitate and just don't stay and back. And the other thing I would like to add with this one more initiative is, like, this is an era of golden period in the sense of the university when it got IOE, and which helped us in several sense. One of the things is upgradation of lab and adding certain equipment. So today what happened, actually we took certain initiative starting this lab inauguration which happened. Some of you have witnessed correlative microscopy and digital learning center. These two things were very well supported by IOE, and I remember this all happening couple of years ago when we had this IOE, how to say, project sanctioned to different faculty in the interdisciplinary sense, where myself and Sudarshan and Sairam Krishna came together to write a project on correlative microscopy, and that ended up in the scenario today. I would say we have some correlative microscopy related equipment and upgrade and facility here, some of them in IIT Hyderabad very well, and there are some other institution in Hyderabad. So microscopy somehow has become a very big, how to say, imperative and buzzword to get into it. And also for the material sciences is very important that you look through the microscopy. So this is one of the tools. For example, every, how to say, boy or a kid would like to have the, how to say, toy. So this is the toy we are looking forward, and we have not many now. So I'm very happy with that. You know, you play a cricket, there is a cricket means you have a bat and ball, and then you just team starts working. So this is something we have come to that stage. Probably from now on, we will be doing more things in this, because IOE also have several equipments in the interdisciplinary center where School of Engineering have been instrumental, thanks to Professor Ghanshyam Krishna. I think it's almost 5 years ago we took that initiative that, okay, we would like to have all such big equipment. Finally, they are in place. So I don't want to take too much of words. I would like to welcome all of you, and this stage is set to listen to the speaker. But before that, I would like to have few words from our how to say, dignitaries on the dais. But at the same time, I will invite Dr. Sudarshan Pani to talk a little bit about the speaker, because he is our the first person. Then we can go on with the other guests.
Good afternoon, everybody. It's indeed a great pleasure to introduce Professor Easo George. In fact, it's a great honor for the School of Engineering to host him. Most of this introduction goes, I'll probably start off on those lines, because his profile is there for everybody to look up online. Professor George obtained his BTech degree in Metallurgical Engineering from IIT Kanpur, and went on to pursue his PhD at Pennsylvania. And of course, as I said, needless to say, rest of his accomplishment, but simply put, is one of the foremost authorities in the world in the field of alloy design and mechanical behavior. And the metrics are there for everybody to see. He's got hundreds of publications and more than 30 or 40,000 citations, and the list goes on. And he has made some seminal publications, works, or contributions to the field of intermetallics, and also in high entropy alloys. So that's obviously a quite accomplished academician and researcher. And professionally also, he has held several positions at the Oak Ridge National Lab, including being a distinguished staff member and also heading the alloy design and mechanical behavior groups. And also he has been governor's chair professor, and he's also been a special chair at Bochum University in Germany. So the list goes on. So, and as I said, I'm not going to dwell on those details, and so is his awards list. But just to give you people who are not from the field a kind of perspective as to what kind of contributions he has made, recently there was a symposium a couple of years ago in the TMS conference. There was a symposium that was specially held to honor his contributions. So we are really very lucky to have him here. And as a closing note, of course, these are all the professional accomplishments, but one thing that does really stand out, and I can vouch for it, is Professor Easo George is an outstanding teacher, and I am very lucky to be one of his students when he was teaching at University of Tennessee. And with that, as I said, I don't want to take much time. I'll set the stage open for the teacher to take it on. Everyone, thanks a lot for being here.
Before we start the lecture, our Vice Chancellor here, I would like to invite him to say a few words.
Very good afternoon to all of you. I want to warmly welcome Professor George for spending his time here. I also want to welcome Professor Balakrishnan Garu, Murali Balakrishnan Garu, Balamurali Krishnan Garu. Lot of configuration. So it's a very beautiful day today. We just inaugurated a very high-end facility in CEST, and I hope this high-end facility will be extremely useful for learning by our youngsters sitting here. And the second part of today's proceedings is to welcome Professor George and listen to his distinguished lecture. And the title is fascinating. The title is Materials for Space and Other Frontiers of Engineering Challenges and Opportunities. Actually, he has covered a lot of interesting things in the title. The title actually, I hope, will talk about the high entropy alloys and some very fascinating properties of that. And I hope we will also learn the physics of this high entropy alloys, how these alloys become so magically fascinating. So actually I have come here just to hear him. I'm fascinated by some of these new materials. You know, in the future of this science, materials and energy, the combination of these two is going to be the real action point. And in the search of new materials, in the search of characterization of these new materials, I think all of us will be very busy trying to understand how these things function the way they do. And our level of understanding will probably be significantly incomplete when we study their properties, because properties are really not intuitive when you study them. Many things unintuitive or counterintuitive happens. So I really want to welcome him, and we are all here to hear you and see how we can benefit from your presence. I hope my youngsters will interact with you. I don't know how long we'll be here.
Is here today.
So it is a very good opportunity for youngsters to interact with him and learn about some intricate details of material science, the way they are generated, the way they are characterized, and how functions are read out. Thank you very much.
Thank you, sir. Thanks a lot. May I now invite Dr. Balamurali Krishna to say a few words, please. Maybe you can become a professor also here.
Professor B.J. Rao, Professor George, President Krishna, Professor Gautam, all my colleagues here, students, very good evening to all of you. So it's indeed my pleasure to be here. And just as we were discussing, very happy to see CEST grow from strength to strength. I was here long back, 2008-9, teaching the characterization course as part of CEST. From there, things have gone on so much, so many equipments have come, people have come. Professor Gautam talked about 12, magic number and all that. So we would like to see the 12 go much more also. And in terms of students, there are 60 students, plus 16 computers. So it's very, very heartening to see all of that. And just to echo what Professor B.J. Rao was telling, probably you are all very fortunate to have Professor George here, and I am also eager to listen to him. And of course, materials have always defined civilization. You go to Stone Age, Iron Age, Bronze Age, whatever, in between it came Information Age. But still at the heart of Information Age is still semiconductors, optical fibers, and so on. And we are living in a physical world which is full of materials, and the world does not therefore exist without materials. But engineered materials, advanced materials, and as we go forward, question of sustainability, I mean the material sustainability and prosperity together, I think that's very, very important. And a place like University of Hyderabad, where practically any discipline that you can imagine exists, offers you this opportunity of very quickly putting together multi-departmental, interdisciplinary team to look at complex problems, which is what you'll have to do as you go forward. It's my feeling that shared by many people, that this discipline boundaries are going to become more and more diffuse as we go ahead. And so it would be my request. And for the youngsters, especially, you are in very challenging and very exciting times. We need to be very agile. We still can't afford the timelines that we used to take earlier. We used to take 15, 20 years to develop new materials, new class of materials. The requirements today, and of course, new techniques have come up like integrated computational materials engineering, and then the infusion of artificial intelligence and data science and machine learning, and almost all the characterization tools that we have, whether it is structure, property, whether it is functional or mechanical, all of these are digital tools, which means they generate a lot of data. So how to interpret all of this? But the biggest ingredient is the biggest ingredient that the human beings have had forever, which is a sense of curiosity. So I think I would urge all the youngsters here to maintain that urge of scientific temper and curiosity. And I hope that we will all get stimulated by listening to Professor George. Wishing you all the very best, and thank you for giving me this one.
Thank you, sir. Thanks a lot. May I invite now Sir Ghanshyam Krishna, please, because this lot of things are possible because of you who've been supporting. Wherever I go, ask something, you have been, always assertive. Okay, let's go ahead about it. So thanks a lot, and thank you for being here. Few words, sir.
Good afternoon, Professor George, Professor B.J. Rao, and myself, Dr. Malapati Krishna. Professor Gautam, very often when I come to these, and somebody says, I have done something, I wish it was my money. Life would have been very different.
You are the gatekeeper.
Anyway, jokes apart, I thank Professor George for accepting our invitation. And I think one of the major things that has happened as part of the Institution of Eminence program is that academic units have been able to, not only think, but actually invite very eminent people. And this has been a success story of the IOE program. And we have had more than 70, 75 people in the last couple of years, including Nobel laureates and very, very eminent people across disciplines. And that has been the success story. And I'm very happy that the IOE program has contributed to the growth of the university in the last 3-4 years. So that is all I have to say. I hope in all these lectures, the thing that I always urge, and as Dr. Bala said, this is for the benefit of the students. It is for you to take advantage of this. We have our own conversation, but students have to listen carefully, interact, and learn from these lectures. So wish all of you all the best, and again, thank you for giving me this opportunity. And I would also like to say that I've been associated with CES before it was established. So I have very fond, very not just memory. I've been associated with it for a long time, and I'm also happy that in some way I have contributed to its growth. And so thank you for the opportunity, and have a good listen to the lecture.
Okay, so nothing in between now. I will invite Professor George to take the stage and all yours, sir, and keep on coming. I would simply say that it's important, like as doing or IIM, whatever you call it. Thanks a lot.
Explain this is spoken. No cost.
So first of all, I want to thank everybody for being here. I also want to thank the university for very generously inviting me to this very special lecture. I hope I don't disappoint. There have been very many eminent speakers before me, and so please bear with me. So thanks, Professor Gautam and Dr. Krishnan and Professor B.J. Rao and Professor Kancham Krishna. And of course, Sudarshan Pani, where is he? Oh, there he is. He's been a long time friend, and so thanks, Sudarshan. Okay, so I'm going to talk about, there's too much to cover, so I've selected a few things in my life, in my research career, that looking back, I think were exciting and interesting, and I hope will inspire the young students. There are a combination of things that are scientifically interesting, so you get a sense of the wonder of science, but at the same time have practical application, because we're, after all, getting money as scientists. We're not artists, we're not painters, so we get money from the taxpayer. And so we have to show that we're doing something useful. And it's nice every once in a while, or 2 or 3 times in your lifetime, to show that maybe you're doing something useful. So I'll show you one example or 2 examples where things might have turned out to be useful. And I'll try to address some of the challenges and some of the opportunities that are ahead of us. So I'm going to start off with power needed for spacecraft that are sent out into the outer planets. So things that explore Saturn or Pluto, and now most recently Mars, and so on. And just a brief introduction on the various kinds of power that you need. So obviously the first thing you need is you need to launch, and so you need big rockets, huge rockets. Some of these things are very heavy, and so you need things like Saturn V rockets that will shoot it out at escape velocity. And then you need power to cruise. I'll talk a little bit about that in the next slide. And you need things like gravity assist, because even with the biggest rocket, there just isn't enough power to get it out to the outer planets. So you need gravity boosts from other planets. Then you need power for navigation, and those are things, engines and thrusters, ion propulsion, and so on. And so those are relatively smaller scale things. And then if you want to finally stop and orbit a planet, then you need to brake, because these things are traveling at 25,000 miles per hour, very fast. So if you don't slow it down, they never get captured by for braking. And then finally, there are lots and lots of onboard instruments, because some of these satellites are launched once in a scientist's career, They spent 30 years working on a mission to Saturn, for example. So they want to load it as much as possible with as many instruments as possible, so that you can study over the life of the mission. And so you need electricity to power these instruments. So just as an example, this Cassini mission, which went to Saturn, was launched on a Titan IV rocket in 1997. Right, so this is the solid booster rocket, and the satellite sits up right over there. It's a tiny satellite by comparison, and the path taken by Cassini is a very complicated path. So, for example, it was launched in 1997 from Earth. It goes around and it flies past Venus in 1999. So, and this is the gravity assist that I was talking about. So, some of the momentum of this large planet is transferred to this much smaller satellite, and so as it's swinging past it, it gets captured a little bit by the gravitational field of the planet. The planet then pulls it along, but it doesn't capture it into orbit. It just, it's like a slingshot. It goes past it, this planet slows down a little bit, but the satellite speeds up much faster, right? So, and it does this a few times. It flew by Earth once, then flew by Venus again. Each time it gains a little bit of velocity. Each time it goes past the planet. And eventually it flew by Jupiter back in 2000. So this was launched in 97, in 2000, and then it finally reached Saturn, and it went into orbit around Saturn in 2004. So these missions are very long-term missions. So you need sort of almost 5 years just for the travel. And then once it's there, the experiments take another 10, 15 years and so on. So you're talking about missions that have to last decades long. So you need power that can sustain for long periods of time. And so think about the various sources of power that you can provide. Batteries are obviously one source of power. So what you do in a battery is you store energy that you make on Earth, and you separate out depending on what kind of battery it is, and then you release it as electricity in space. But there is no extension cord that you can plug this battery in, right? So once the battery discharges, that's it. So after a few months, the battery loses power and you can't use it anymore. Fuel cells are somewhat similar to batteries. The energy is stored separately as hydrogen and oxygen, for example. And then when you bring the hydrogen and oxygen together, you form H2O, and that releases energy, and you can use that. But what it means is that all the hydrogen and oxygen that you need have to be transported up, and you'll never be able to launch the satellite because it's too much. So batteries and fuel cells are good for short-term missions, but not for long-term missions. Solar panels, obviously, for near-Earth orbits are fine because you can use solar power to convert to electricity. The problem is the further and further away you get from Earth, the less the solar intensity. And so by the time you get to Saturn, the size of the solar panel that you will need would be way too big, and you'd never be able to launch it. And so solar power doesn't work for deep space. So what is typically used is something called a radioisotope thermoelectric generator. And what it does is it converts the decay heat of a radioactive element, for example, plutonium. And this plutonium, as it decays, is sitting there red hot. And now you have the cold junction of outer space. And so you can take the temperature difference, and by the Seebeck effect, which is like the reverse of the thermocouple effect, and you have dissimilar metals connecting the hot junction to the cold junction, and you have an electric circuit. and it generates an EMF. And the advantage of this is there are no moving parts, right? There's no turbine, there are no mechanical gears, nothing. There's just thermoelectric conversion. And we know the half-life of plutonium is about 87, 88 years. So we know exactly how the power is going to decay. So the physicists can calculate what the power requirement is going to be 80, 90 years in the future and how much power we'll need. And so it's a very reliable source, and this is what I'll talk about. So this is just a picture of what the Cassini spacecraft looks like. So just to give you an idea of the scale, this height here is about the size of a bus, right? So this is like the size of a bus. At the bottom here, these are the 3 thermoelectric generators, and that's what one of those looks like. And this is approximately the size of a sofa at your house. So this is just to give you a scale. And then there are all these different kinds of instruments on board that this will power. Now, if you zoom in on this one, just another example. That was Cassini. This is the Perseverance rover that is currently on Mars. That's exploring Mars. And this is also powered by this radioisotope thermoelectric generator that's sitting over there. And it's got all these other kinds of instruments on board. And unlike other rovers that are small and didn't need a lot of power, this requires a lot of power because they're drilling down into the rock bed and getting samples out and stuff. So without this nuclear power, you just wouldn't be able to power it. And that, like I said, that's what that power source is. And this is what it looks like when you blow it up. And some of the earliest RTGs, which are multi-hundred watts, are still functioning on Voyagers 1 and 2, which are now outside the solar system. They're out in interstellar space. And so they were launched more than 45, 50 years ago, and they're still sending signals back. So they're very, very reliable. It's amazing. Now, when you zoom in on this thermoelectric generator a little bit more, then you see that there's, in the center here, there's, these are the plutonium heat sources, right? And these are this is an earlier version of the thermoelectric. These are silicon germanium thermoelectrics. The newer ones are gallium arsenide, but the silicon germanium, so one end of the silicon germanium sits on the hot source. The other end sits on the aluminum fins sticking out into outer space. And so that's the cold junction. And just that temperature difference between the hot and cold junction generates enough electric power. And then they're stacked together like so, multiple units of these. Each individual stack looks like this. So there's the plutonium that is sitting in here, and they're 2 together. They're put into this sleeve here, and then another one is put into this sleeve, and they're all screwed in place together. And then when you look at one of these a little bit in a zoomed in view, this is what one unit looks like. This is the plutonium oxide fuel pellet, which at steady state is sitting around 1300, 1350 degrees Celsius. And these are the 2 cups that are made with iridium metal. And the iridium metal is clamped around the plutonium, and then you weld it shut. There's a weld shield that goes in here, because when you weld it, you don't want to accidentally blow up the plutonium oxide. And when you put all this thing together, then this is what each pellet looks like. And the reason you need iridium is if there's an accident during launch, you want to protect the plutonium, right? You don't want the plutonium to spread out all over wherever the nearest launch site is. And so it's a protective mechanism. The engineering design is actually pretty complicated, because as the plutonium decays, it generates helium as a decay product, and this helium has to then be allowed out of the pellet it cannot be hermetically sealed because otherwise, eventually, the gas pressure would make the pellet explode. So you want to be able to release the plutonium, the helium gas, but it has to be filtered through a frit. Otherwise, it might take some of this plutonium is not metallic plutonium, it's an oxide. So you don't want any of the oxide fines to escape, right? And so it's a pretty complex engineering design. But more impressive is the operating requirements, right? So you have to spend years at 1300 C. You have to spend minutes at around 2000 C. And the reason is if there's a launch accident and it fails, then it'll come back through the atmosphere, and during re-entry, the temperature will rise to around 2000 C during re-entry. So you need this capability to withstand a few minutes at 2000 C if there's an accident. It has to be compatible with carbon and oxygen because outside this, it is encased in a graphite insulation. So it has to be compatible with carbon on the outside. And because it's a plutonium oxide, there's always a partial pressure of oxygen on the inside. So it has to be compatible with oxygen on the inside. So if you know your Ellingham diagrams, you know that in thermodynamics, there are very few materials that are compatible with both carbon and oxygen at 1300 C for years at a time, right? And then it has to have high strength in case there's an accidental impact, and it has to have good impact ductility if it for whatever reason, there's an accident and it crashes into Earth. So when you look at the periodic table, right, there are just a handful of elements that have melting points that are greater than 2000 C. So you're kind of limited. Nature limits you in what you can use. These elements, niobium, moly, hafnium, tantalum, tungsten, these are the refractory BCC alloys. They are not oxidation resistant. And so they will not survive. Ruthenium, rhenium, and osmium are HCP crystal structures. So with HCP, you know that it has brittle fracture. So that kind of leaves only one element, iridium. It has a high melting point, about 2450 C. It has the FCC crystal structure. So it's ductile, relatively, with some exceptions I'll talk about. It's compatible with oxygen and carbon, and it has decent strength. So just some fun facts about iridium, in addition to the metallurgical aspects. Some of you may know that a lot of optical fibers and optical crystals are grown in crucibles that are made with iridium. And so this iridium crucible is about that much in diameter, that tall, and then you use Czochralski pulling to pull fibers out of it. So very reactive fibers made with very reactive oxide melts are grown in iridium crucible. This is a used crucible, and you can see that at high temperatures about 2000, there's a lot of creep damage that occurs in these materials. They're used in high performance spark plugs. So if you buy a very expensive race car that has spark plugs in it, or in piston driven aircraft, these spark plugs have iridium tips there. They're used in rocket thrusters. If you're rich, you can buy fountain pens that have nibs with iridium, and of course, some people like to use iridium for jewelry. The earliest satellite phone was made by Motorola, and it was called the Iridium satellite phone. Any guesses on why it was called the Iridium satellite phone? It was not made with iridium, by the way. Well, the atomic number for iridium is 77, and initially their plans called for 77 low Earth satellites in orbit around the Earth to cover the Earth. But then there were budget cuts and everything, and the number of satellites dropped to 66. And then you look up the periodic table, and the element is dysprosium, which doesn't sound as exciting as iridium, and sounds like something you might take for a stomach upset or something like that. So they still call it the iridium program. But most importantly, iridium killed off all the dinosaurs, right? As some of you may know. So if you look, Walter Alvarez, who got the Nobel Prize in Physics, and his son, who was a geologist, had this theory that there was a giant meteor strike that hit the Earth around 66 million years ago that wiped out, that caused global climate change, which then caused eradication of all the dinosaurs. And if you look at the boundary, so if you look at certain parts of the Earth, right, and it's not just in one location. There's locations all around the globe, and these are some of those locations that are marked here. But the most famous one is this one in the Gulf of Mexico. There's a huge big crater in the ocean, in the Gulf there. And if you measure the iridium concentration up to about 66 million years ago, right, the iridium concentration is almost zero. And then all of a sudden there's a big spike in the iridium concentration, which is a very narrow range. And it's not something you would expect from normal deposition over glacial time periods. Oh. Rather, it happens in a very narrow region, and the theory is that there was a giant meteor that contained high levels of iridium. All these heavy metals exist mainly in outer space, in meteors, right? Because all the heavy metals that existed on Earth have been absorbed into the molten core of the Earth, and there aren't very many heavy metals left in the Earth's crust, right? So anything that you discover on the Earth's crust that's a heavy metal came from meteor impacts. Okay, so with that background, iridium is an interesting metal because unlike most FCC metals, it shows a ductile brittle transition. So if you plot, this is at slow strain rate, so 10 to the minus 3 per second strain rate. It shows somewhat decent ductility at room temperature, but then the ductility improves dramatically as you go to high temperatures. This is unusual because most FCC metals will be flat like this, right? Most FCC metals don't show a ductile brittle transition, so this is more like a BCC metal. But when you change the strain rate from 10 to the minus 3 to 10 to the plus 3 per second, so 6 orders of magnitude change in strain rate, this is what happens to the ductile brittle transition. But you have to look at this scale. This scale is quite different from this scale. So the low temperature ductility is very low. It's like here, but at high temperatures, the ductility never gets up into the 50-60% range. The ductility is still around 10 to 15%. So you don't get a significant improvement in ductility in pure iridium. But if you dope with a small amount of thorium, and this is about 200 ppm thorium, it shifts the ductile brittle transition dramatically. Right? So all of a sudden, and these were experiments done in an impact gun where we fire a bullet, and we can do experiments in tension at strain rates of 10 to the 3 per second. And without the thorium, you get mostly grain boundary fracture, and with the thorium, you get transgranular fracture. And we understand now the mechanism, how thorium improves the ductility. It does two things. Actually, it does three things. The first thing it does is that we look at the iridium-thorium phase diagram. The solubility of thorium and iridium is almost zero, right? So the tiniest amount of thorium comes out as iridium-5 thorium intermetallic precipitates. These precipitates then refine the grain size because they pin the grain boundaries and they prevent the grain size from getting too large, and that's one way. But the thorium also segregates to the grain boundaries. So if you plot the amount of thorium on the grain boundaries as a function of the thorium in the bulk, it rapidly, around 5 ppm thorium in the bulk, it rapidly saturates. And then beyond that, you don't get any more thorium on the grain boundaries. And that's because the solubility limit is so low, right? So anything above 5 ppm ends up as a precipitate. So below 5 ppm, it saturates all the grain boundaries. And then if you plot the ductility, elongation to fracture, of all the undoped alloys versus all the thorium doped alloys. So you can take thorium from 30 ppm all the way to 1000 ppm, right? What you find is all the thorium doped alloys fall on one curve and all the undoped alloys fall on one curve, right? And the way the reason I plotted this as a function of inverse grain size is because now you can separate out the intrinsic effect of segregation to the grain boundary from the grain refinement effect. So to study the grain refinement effect, you go down this axis and you pick any one grain size and you go up and you find that for a fixed grain size, the undoped material is always more brittle than the doped material. Okay? Or the other way to look at it is if I pick any one grain size, any one thorium concentration and change the grain size. This is inverse square root of grain size. So this is decreasing grain size here and decreasing grain size there. So this move along this line here is a grain size effect, and this difference between this curve and this curve is the grain boundary segregation effect. And as I said, it suppresses the grain boundary fracture. So down here you have mostly grain boundary fracture, right? And as you go through this ductile brittle transition, it transforms from mostly grain boundary to mostly cleavage transgranular fracture. So suppression of this grain boundary fracture is the reason why you get this you get this thorium effect. And then you can put all this together and you say, well, if I look at all the quasi-static tests, the tests at 10 to the minus 3, and you do all the bullet tests at 10 to the plus 3 per second, you can see the dramatic shift in the ductile brittle transmission. So, and the reason why this high strain rate is important is because if there's an accident, then this thing is going to plunge down and hit the earth at very high strain rates on the order of 10 to the 3 per second. And so this is why you have to worry more about what happens under these strain rates than this strain rate. Okay, so I want to switch a little bit now to materials that are used for engines. So this is just a schematic of a modern gas turbine engine, and you can see that over time, if you go from 1965 to say 10 years ago or so, there have been systematic improvements in alloy development that have increased the temperature capability of nickel-based superalloys all the way from about 800 C or so to something like 1100, this is 1000 C, the metal temperature. But in addition to that, you have these thermal barrier coatings that you put on the superalloy. And this is a ceramic which acts as an insulator, and so that improves the ductility. The temperature capability. And then over time, they also had active cooling in the blades, so that you could blow air through the holes in the blade, and then that will cool the blades further. So combination of thermal barrier coatings and the film cooling from the active cooling, you now have temperatures, the inlet temperature of the gas coming out of the combustion chamber that's hitting the first, the high pressure turbine blades is above the melting point of the metal, right? So it's quite dramatic what the improvements have been. But you can see that most of these alloys, as they've developed, they've always sort of approach this plateau-like behavior, right? And so the current alloys are similar to what is called a CMSX4 alloy, which is a single crystal alloy that GE uses. It was originally patented by Canon Muskegee, but several engine manufacturers use it. It has an operating temperature around 1100 C, give or take. And the reason this alloy is so effective at high temperatures, it's actually a composite structure. It is a two-phase structure. It's got these little cuboidal precipitates that are this ordered gamma prime, ordered structure that looks like this, where the nickel atoms on the face centers and aluminum atoms on the cubes or the corners, and then the regions in between, the thin regions in between, are the disordered FCC phase. So it's mostly a FCC gamma solid solution. The volume fraction of this of the second phase can be as high as 70%. So very high volume fraction of second phase precipitates. And then if you look at the properties of the FCC versus the gamma prime, you see sort of very interesting differences in behavior. So if you look at the nickel, pure nickel gamma, this is what the yield strength looks like as a function of temperature over a very large temperature range. So almost practically no temperature dependence on yield strength, right? So it slowly gets softer as you heat it up. And if you look at a blacksmith making tools in the old days, they would take a piece of steel or whatever, put it into fire, it gets red hot, you take it out and you beat it, right? And the reason is because most metals get softer as you heat them up. But this gamma prime does the opposite, right? So this is this nickel to aluminum gamma prime ordered phase. So here's how its strength increases with temperature. So you have the best of both worlds in the sense that you have a strengthening precipitate that actually gets stronger as you heat it up, and you have a matrix that remains ductile over the entire temperature range. And that's why these two-phase alloys have been so successful. So several years ago, we started looking to see whether there were other systems, not at the high temperature nickel system, but iron-based systems that are used at lower temperatures that might show the same effect. And surprisingly, there are some systems that show the mechanism is different. In the nickel to aluminum case, the reason for the temperature dependence is because of dislocations, cross-slipping and getting caught up during the cross-slip process. Here it's due to vacancies. And initially, people never saw this unusual temperature dependence. So this is what it looked like. This looks like the sort of traditional BCC-like behavior. We have a strong temperature dependence here, but relatively flat region over here, and then a drop-off at high temperatures. But the reason is these alloys have a lot of quenched-in vacancies. Now you might think, well, why didn't people think about getting rid of the quenched-in vacancies? It turns out it's not so easy to get rid of the quenched-in vacancies at FeAl. And that's because, unlike most materials, where the migration enthalpy of vacancies is is low, but the formation enthalpy of vacancies is high, which means that it's very difficult to form vacancies, but very easy to move them in most metals. In FeAl is exactly the opposite, meaning that it's very easy to form vacancies, but very hard to get rid of them. So you have to anneal it for weeks on end at very low temperature to get rid of the vacancies that are frozen in from high temperatures. But when you do that, what you find is that you get this behavior. You get this anomalous behavior, right? So immediately our question was, is this because you're generating new vacancies? You've got rid of the vacancies. Now, during the heat up to the testing temperature, you're generating new vacancies. And is that the reason for this increase in strength? And sure enough, it is. And the way we showed it is by doing path-dependent experiments. So you could test at the peak temperature. So if you want to test at this temperature, you could approach that from the high temperature side, or you could approach it from the low temperature side, right? So, and if you approach it from the high temperature side, you've already quenched in the high vacancy concentration that has been set at the high temperature. But if you were able to rapidly heat from room temperature up to this, then maybe if the heating rate is fast enough, then you maintain the low vacancy concentration. And that's indeed what we saw. So when you upquench very fast, you get very low yield strength, you up quench, and then you hold for a little bit longer, the yield strength goes up, you hold for a little bit longer, and then you vacancies, which is representative of where you quenched it from, and so on and so forth. So just to quickly, I won't go into all the details, but you can use simple expressions for hardening due to vacancies using a Fleischer type model, where the vacancy concentration to 1/2 times some constant times shear modulus is the yield strength, and the vacancy concentration then depends on the formation energy of the vacancies. And the high temperature strength just is described by a creep equation, right? And I won't go into the details. But this depends on both the migration and the formation energy. This only depends on the formation energy. And so you can simply use these expressions to model what the behavior should look like. And I won't go into this part, but here, this dotted curve is the model predictions, assuming what the vacancy concentration is that you can measure independently using positron annihilation experiments, for example. So the vacancy concentrations can be measured independently, and you can fit it to this. And so this increase is due to the increase in vacancy concentration. But the same vacancy concentration causes weakening at high temperature, because creep is mediated by vacancies, right? So these are the creep equations. And of course, this is not strain rate sensitive, but this is strain rate sensitive. So the faster the strain rate, the more the curve shifts to the right. So you can easily see that and imagine that. And so which means that if you now draw a curve at different strain rates, you will see that the peak temperature will shift to the right, and that's in fact what we see. The peak temperature shifts to higher values and to the right as you increase the strain rate. Okay, so now I want to talk a little bit about another interesting phenomenon, which is that smaller is stronger. This was a very popular thing a few years ago. So you know, in most materials, we know that if you take a chair and you want to make it stronger, you make the legs bigger, right? And you make the thin, spindly legs, and it'll get weaker. But what Mike Uchek and Dennis Dimitak, who were at that time at the Air Force Research Labs, showed was that if you make pillars of different sizes, and they made these pillars by nano fibbing, so these are different size pillars that they fibbed out of a large single crystal. These were made out of nickel, and then you deform it. You take this pillar and you deform it using a flat top nano indenter, not a conical or a Berkovich indenter, but an indenter that had a flat top machine on it, and you push down on it, and it behaves like a single crystal. So you can see that you get very nice, initially single slip. It depends on what the orientation of the pillar is. And then they plotted this as a function of pillar diameter from 1 micron to 30 micron diameter. And what you find is when you get to about 30 micron pillar diameter, you get flow stress that behaves like this. And this is very similar to what the bulk flow stress of nickel is. Right? So if you took a bulk sample that was millimeters in size and you plotted the engineering stress strain curve, that would look like this. But then when you go to 1 micron diameter, then the strength increases dramatically. So the smaller pillars were dramatically stronger than the bigger pillars. The other interesting point that they noticed was that when you take the big pillars and you test many of them, the scatter in the data was very small, right? They all behave like each other because of an averaging effect. But when you looked at the small pillars, the scatter in the flow stresses was quite large. If you look at all the green curves, you'll see that the scatter in the flow stresses is quite large. So those are the two interesting things that they discovered. And around this time that they were reporting this data, I was just lucky that I was on their on their advisory panel evaluating the metals program at the Air Force Lab. And so I went there, and so I was fascinated by this result. And so it was a 3-day evaluation. So they presented all the data, and I asked them, so, okay, so if you have pillars that are 1 micron in size, and you have a well-annealed single crystal, 1 micron, right? The pillar should on average contain no dislocations. So a 1 micron pillar should contain no dislocations. So why is it that you're not getting the theoretical strength? The theoretical strength should be on the order of gigapascals, not megapascals, right? And it turns out they hadn't really thought about this very much. So they said, oh, that's an interesting point. And so I came back to Oak Ridge, and we started with George Farr, started looking at this. And so here's a simple picture of what you might expect. So imagine that you have dislocations, and it's a very ordered array, just for simplicity, it's a cartoon. So you have 2 length scales. One is the spacing between the dislocation, and one is your pillar space, the size of the pillar, right? So in one case, if your pillar is so small that it entirely falls between these other dislocations, there'll be no dislocations inside the pillar. Or you could go to very large pillars, and in which case you have lots and lots of dislocations, right? And on average, you would behave like a bulk. Here you would behave like ideal single crystals, like Brenner's classic paper. And then if you're in between, right, then all the statistics of dislocations and the activation energy, the stresses need to activate dislocation, all those come into play. So you get a distribution of sizes in this range. You get one strength in this range and another strength in this range, which is sort of deterministic, and here it would be statistical, probabilistic. So just to put this in a cartoon format, so if I plotted yield strength versus the specimen size, at very low specimen sizes, you would get strengths that are close to the ideal, which is G over 5 to G over 30, which is a theoretical strength. And at very large pillar sizes, you get bulk strengths, which are G over 1000 to G over 100. And then there'll be some transition between the two, which we don't quite know, but let's imagine that it looks like this. And just as luck would have it, around that time, I was working on directionally solidified eutectics. And one of the systems that we were looking at was nickel aluminum with moly fibers. So these are molybdenum fibers in a nickel aluminum matrix, and we were directionally solidifying them in an optical floating zone furnace. And by changing the growth rate, right, when you grow them faster, the pillars get smaller and closely spaced. When you grow them faster, they get bigger, right? And then the matrix, the nice thing about this system was that NiL reacts only to acids and molybdenum only reacts to bases, right? So you can selectively etch the matrix from the pillar, from the fiber, and when you etch it, you end up leaving behind these perfectly pristine molybdenum fibers or pillars, right? And the nice thing about this is, because you don't have fibbing, there's no fib damage involved in it. You get, in principle, you should have pillars with no dislocations in them. And so we tested them just like UCHIP did. And here's what we find, right? So we find that the stress strain curves, this is load now versus displacement. So small pillars look like this, the intermediate ones look like this. And so all the way from 360 nanometers to about one micron, right? So if you look at the loads, they look like the smaller is getting stronger, but it's not the load that is important, it's the stress that is important. So when you divide by the cross-sectional area, these stresses are almost identical, right? So there is no smaller or stronger effect. They all yield at close to the theoretical strength, 10 GPa, give or take. And so these are the pillars from small to large. And so that sort of solved one of the puzzles of the UCHIP and Dimiduct data. Smaller really is not stronger. What they were seeing was the effect of defects in their pillars. So now we could take these pillars and extract it completely from the matrix. So now you dissolve the matrix away completely, and you're left with these very long fibers, right? And with the help of people in Germany, we were able to then test them in tension, not just in compression in the nanoindenter, but in tension. So this is what it looks like. You can pull on these fibers, and we saw something very interesting. So if you look at the compression pillars, right? The data are scattered, but not very badly scattered. They're all about 9 GPa plus minus a tenth of a GPa or something. But the tensile yield strengths are scattered quite a bit. Right? So they go all the way from what you would expect a bulk to behave like to what a perfect crystal would behave like. And the reason is because the size of this pillar is different from the size of this fiber. This fiber is quite a bit longer than this. And so the probability that you would find a pre-existing defect in this is much greater than in here. And that's in fact what Sudarshan Pani and his colleague showed. So if you look at lots and lots of fibers, you do TM on them, and what you find is that in many areas they're completely defect-free, but every once in a while you'll come up with little bundles of dislocations that show up, right? So when you grow this as a single crystal, it's not a perfect single crystal. So every once in a while there'll be defects in there, and Fani was able to very painfully measure the spacing, average spacing between this group and another group over here, and the average spacing was about 37 micron, which will be roughly 1 over the square root of the dislocation density. Okay, so then the next thing he did was he developed a very simple 1D model for the tensile test, which I think is very clever. So there are, again, 2 length scales in the problem. One is this size of this pillar that you cut out, and the other one is the average spacing between the dislocations, right? And this, remember, is 37 microns because we measured it already, right? So if you cut a pillar from this region, you should get the theoretical strength. And if you cut a pillar including this, then you should get the bulk strength. This is a very simplistic picture where the bulk strength is equal to the critical result shear stress to move that dislocation. So you would go from either here, from here to here, right? And then depending, and if you do a Monte Carlo simulation, right, of uniformly spaced dislocation, and you do lots of simulations, right? Sorry, before you do the Monte Carlo simulations, you could now then do a weighted average of this one and this one, where this is the bulk strength multiplied by this ratio of L over L bar, and when L is large compared to L bar, which means the specimen length is large compared to L bar, then this term dominates, sigma bulk dominates, and you would get things that behave like the bulk. In the other case, this one dominates and you get behavior that looks like this. And then this equation is simply this one, right? But these don't have to be distributed uniformly. There could be a Poisson's distribution, right? And this is what Connie did next. And then this is the solution to the Poisson's distribution. I won't go into the details. And now you could add one more complication. In addition to a Poisson's distribution of dislocations, you could give each dislocation an activation strength, right? Each dislocation moves only when you apply a certain stress to it, right? And so this is a combination of random spacing and orientation. This one, unfortunately, doesn't have a closed form solution, but you can get a numerical solution to that, and that's what this looks like. And so if you now do this Monte Carlo simulation for these different cases, and these are again Pani's results. So when you have the size of the specimen is small, if you do 30 simulations, they all land right on one top of each other. If you're way over here, very large specimens, they all line one on top of each other. And then somewhere in between, you'll get this distribution, right? But what is interesting about this distribution is not that once you cross into this boundary, that these distributions are uniformly distributed. Actually, the closer you are to the upper bound, the more the data points are clustered over here, and the closer you are to this lower bound, the more the data points are distributed, clustered around there. And this is just the envelope of the upper bound, and this is the envelope of the lower bound, and all the data falls in this region. And now, when you take the Monte Carlo simulations and you superimpose the experimental results, yeah, this is what you find, right? So where you would expect all the data to be clustered together is in fact where the experimental data cluster, and then where you would expect them to be distributed in this region in the middle, this is where the data are in fact distributed. So in addition to these two other length scales, right, where you change the size of the specimen, making them smaller or larger, you can also change the spacing between dislocations. So this is well annealed crystal. This is crystal that has some core work in it, and this is crystal that has a lot of core work in it. And what you would find is that as you take the same specimen size, then you would sample more and more dislocations as you had more and more defects in them. And this is what you would expect, that curve, when you go from theoretical to bulk, this with increasing dislocation density, you would expect that curve to shift to the left. And that's in fact what we see. So we took material that was initially grown, and then we gave it core work of different amounts. And when you have 0% pre-strain as grown, so all the data fall very close to each other, theoretical strength about 10 GPa. When you have 11% pre-strain, you have so many dislocations in the material that behaves like a bulk. Again, no scatter, so no scatter here, no scatter there. And then in between, at 4% strain and 8% strain, you get this scatter, right? Which is, so you get probabilistic behavior when the specimen length scales approach the defect length scales, and the two extremes, then you have more deterministic behavior. And so this is what it looks like when you compare the tension and compression data. They all behave kind of similarly. So if I have a few more minutes, okay, I'm running late, but let me quickly then jump forward. So since somebody mentioned they're interested in this high entropy alloys, so the term was coined in 2004. Since then, it's really taken off. This is not the most recent data, but you can see the number of papers and the citations have both increased dramatically. In recent years, it's even higher now, but I haven't got the latest data. So just to put things in perspective, in a conventional alloy, you have a primary solvent. So if you have an aluminum alloy, aluminum is the solvent, and then you add things like silicon to it, secondary elements. And they occupy the corners of the phase diagram, right? So this is the ternary phase diagram. These conventional alloys are in this corner. High entropy alloys are kind of in the middle of the phase diagram, right? So there's no solvent or solute in the conventional sense. Multiple principal elements, and there's just a vastly greater number of these alloys in the tens of millions rather than this a few thousand in the corners, right? This by the nature of the combinations that you can get. So a lot of this is unexplored. And there are many claims, some might say hype about high entropy alloys. The first is that configurational entropy stabilizes solid solution. This was the founding hypothesis of the field, Ye's original paper. And then some people think that you have entropy-driven sluggish diffusion because of the rugged potential energy landscape. Some people have claimed that the higher the entropy, the higher the strength by solid solution strengthening. Most recently, short-range odor has become the hot topic. There's dozens of papers in short-range odor and how it enhances strength and affects foot behavior. And then finally, that some refractory HEAs have the potential to go beyond nickel-based superalloys and so on and so forth. And the short answer to all of this is that practically none of the other above claims are true. I'll show just a few examples. But I want to add a word of caution, right? Which is that it doesn't mean that HEAs have no future as structural materials. At cryogenic temperatures, they have outstanding exceptional properties. And at elevated temperatures, there's some work to be done. We need to beat superalloys, which are like really miracle materials. We need a lot more work before we can have materials that can beat superalloys. So the one unusual thing about FCC HEAs is that both the strength and the ductility increase with decreasing temperature. You know, in steels, for example, we all know the experiment that we do in undergraduate labs where we take sharp impact and bar and put it in liquid nitrogen and hit it, and it breaks like glass. But these FCC HEAs get stronger, but they also get more ductile as you increase the temperature. So this is the strength, this is the ductility, and both of them increase with decreasing temperature, which is an unusual good combination to have. And of course, when strength and ductility increase at the same time, then the fracture toughness you would expect to also increase, and that's what you find. Both the steady state fracture toughness and the crack initiation fracture toughness both increase down to liquid hydrogen temperature, right? So you can get very, very high strengths and toughnesses at liquid hydrogen temperatures. And then if you plot an Ashby plot of fracture toughness versus yield strength, these are the high entropy alloys. These are the toughest materials on Earth, right? So, I mean, you can compare to any other system that people have tested, and they're by far the toughest, approaching 500 MPa square root meter. So the question then is that will these, so at cryogenic temperatures, there's no doubt that, that one can get exceptional properties. The question is, at high temperatures, can we get exceptional properties? And the answer is a qualified maybe. And so this is one that many people have been looking at, and we did creep tests on this, and this compares this polycrystalline HEA with CMSX4, which is the state-of-the-art superalloy, and they're orders of magnitude weaker than CMSX4. But what is surprising is that they're also weaker than the single crystal matrix of the superalloy, right? So this is not so surprising because this is a two-phased mixture. But even the matrix, and that's because this is FCC, this is VCC, and diffusion is much faster in the VCC. Okay, so to summarize then, for cryogenic applications below 100 K, right, the opportunities are that they have outstanding mechanical properties. So the challenge is we need cheaper alternatives. So iron-based alloys, because elements like cobalt and nickel are very expensive, and it's hard to get industry interested in these alloys. Intermediate to high temperature applications for power generation and transportation. The problem is that the melting points of FCC HEAs are similar to superalloys. So given that superalloys are very well established and there's a lot of data available on them, it's going to be a hard sell to come up with anything that will be attractive in that temperature range. For ultra high temperatures, about say 1500 Kelvin, so there's also opportunities in hypersonics, rockets, engines, space, and power. And the challenges are BCC HEAs are weak and creep, so we need precipitation hardening, and there's a lot more additional work that needs to go into these HEAs. And then the iridium that I talked about, I sort of skipped over the fact that the thorium that is added, the few ppm thorium that's added to the iridium, the thorium is radioactive. So there's a lot of interest in finding alternatives for thorium, and we've developed some alternatives for that. But until and unless the use of radioactive thorium becomes environmentally a big problem for us, we will continue to use this, but we've got a new alloy already ready to go in case that's a problem. So with that, let me stop, and I'm happy to take questions. Thank you.
So, few questions, if you have. Yeah. Any in mind? So, if you understand. No? Okay. That's good. Then it brings me to the next part of it. Like I would like to do the felicitation of Professor George. May I request our Honorable Vice Chancellor and guest of honor, Dr. Pradmurli Krishna, to come on the stage, please. So I'm actually happy to see everyone have been silently listening. So that's wonderful. It means everything has gone in the minds. Probably they will apply later. Oh, okay.
That's the last year.
Okay, please. Yeah, maybe have the.
My name is Sundar. It's my classmate topologist. We were studied in Andhra University. I retired from DHL as general manager. So I was dealing a strategic project with the defense. So these materials, any materials are developed for submarine applications. That is made of, because that is not touched upon. Everything is touched about the spacecraft.
Yeah, so, at Oak Ridge, we work with NASA on material for space power. And the reason is because anything to do with atomic energy is handled by the Department of Energy. And we are a Department of Energy lab at Oak Ridge. The naval nuclear program is either handled by the defense labs or by the Navy nuclear labs. And they are completely behind the fence, and they cannot talk about any of that. So I don't know anything. So I'm sorry, but yeah. But since these are civilian missions that are used for, and you can find a lot of that information on NASA open web page. So we work on things that are publishable open web. So a lot of the other stuff is behind the.
Okay.
Yep.
Yes.
Recently, this Airbus accidents worried the entire nation as well as the international level. Recently, newspaper it has come that the software is getting affected with the radiations of the sun. So, do you think it is the correct one, or they want to change the software, but they have not talked anything about the materials? So, do you any research has taken in those lines?
Yeah, so I cannot speak directly about this most recent Airbus incident because I don't think everything is known about it. But radiation hardened electronics have been a big topic of research for a long time, right? So electronics that survive high radiation environments and solar flares are part of that, and they worry about it. Extended space ventures when they're crossing radiation belt and so on. So I think there's a lot of research in that area. It's not my field, but hardening of electronics. I don't know if software, well, whether software also needs hardening, I don't know. But certainly electronics do need hardening against radiation. Thanks.
Yes, sir. Please.
If I look at all your data, the beautiful manifestation of transitions of size, composition, and strength. This is basically solid state physics, condensed matter physics, and beautiful measurements. is the theory behind this being developed? That's the question.
Yes. So, for simple systems, the theory is reasonably well developed. The complications are when you have microstructural length scales, and there the theory is not well developed. And so it will take a while to hand over calculations that are conducted at one length scale on one time scale, and you pass it on to the next time scale and the next length scale. So take MD, for example, MD simulation. They're occurring at the picosecond time scale, right? So maybe people have been able to expand it to nanosecond time scale. So in the first ion impact during radiation damage, yes, you can see what happens to the defect formation. But what happens in the nuclear reactor after 30 years, we cannot predict from the MD simulation, right? And this is the problem in material science overall. And how do you hand over information from one length scale and one time scale to another upper level and upper level, to the point where you can predict the life of an engine, or you can predict the life of a structure. And this is very different. People have been talking about it for the last 30, 40 years, and I have not seen dramatic progress. I may be a pessimist, but I have not seen dramatic progress.
And a couple of fundamental issues. We both talk. When we talk about vacancy and healing, for example, is a classic problem. Because if you have 10.20 vacancy, any of your molecular dynamics or first principles calculations still can't be realistic vacancies also. I mean, orders of magnitude higher to do that. And the time scale is more matching. Because of a very, very slow ability to set at the upside.
Yeah. And you may bring up a very important point, which is that in addition to that, the path dependence is missing in a lot of simulations, right? So you can arrive at a certain microstructure in 5 different ways, right? And they may have an effect on the property. And you won't get, so just by knowing the microstructure, you may not be able to predict the property, because how you got to the microstructure may be also important in some cases.
So none of the properties are state variable.
Right, exactly. I mean, look at even something simple as a stress strain curve, right? You have a stress strain curve that does this, you have the same flow stress here as you have here, right?
Mechanisms of variation.
Yeah. And so how do you predict that? Yes, biology is even more
So the
complicated.
lat learning density, because it is a many-to-many correlation. And time scales and length scales move to be matched for simulation, example,
Well, if it was easy, then we'd all be out of a job. So it's good for you guys, young people. Your job is secure for the next 50 years. Maybe longer, right? But
yeah, you would take these jobs.